We're going to start today on page 490, which is solubility in KSP. Right, solubility is defined as the maximum amount of solute that will dissolve per unit volume of solvent at a given temperature. In tables, you're usually going to find it in grams of solute per mils of solvent. But for our computations, we're going to use molarity, moles of solute per liter of solution, and our solvent is always going to be water. Here's the graph of solubility of three hypothetical substances, A, B, and C, versus Celsius temperature. You can see that A rapidly increases solubility with temperature, and B less so, and C is pretty flat. At 50 degrees, however, B has a higher solubility than A, which has a higher solubility than C. But as we go up above 50 degrees, A is probably going to have the highest solubility, then B, then C. Most substances increase solubility with increasing temperature. However, there are a few substances that do the reverse. If you're into geology, if you're out there digging in various geothermal situations, then you have to be aware of the different types of substances that can actually increase dissolution at lower temperatures. So one such substance would be calcium sulfate in hydride, meaning no water whatsoever. A saturated solution is one that contains the maximum amount of dissolved solute with some extra solute that doesn't dissolve. So it refers to any of the points on these curves here. Okay, so every one of these points refers to the maximum amount of solute that can dissolve in a given amount of solute. That's called a saturated solution. Unsaturated solutions are those that contain less than the maximum amount. And it's even possible, if you're very careful, to create a supersaturated solution, one that contains more than the saturated solution. To make one of these supersaturated solutions, you would have to do things like make sure that you have very pure reagents so that there aren't any extraneous dust particles or other materials in there that could induce crystallization. The water that you use has to be extremely pure, usually filtered through nanopore filters to remove any dust particles that can serve as nucleation sites that can induce crystallization. And you have to be very careful about how you handle one of these supersaturated solutions. If you jar it in any way, if you put any shock on it, it's probably going to crystallize right away. So this would be the saturation curve, what we call normal solubility. At this concentration in molarity, the solution is unsaturated, and if you're careful, you can make this supersaturated solution. Those scientists studying crystal growth often do so by making supersaturated solutions, or if they want to actually to grow very fine, perfect crystals, they'll start with the supersaturated solution and slowly induce crystallization by adding a seed crystal to the mixture, causing the crystallization to occur. So for this section, it'd be nice if you knew something about ionic compounds, and how to write their names and chemical formulas, and their ionization equations, and ionic, net ionic, and molecular equations as well, and know something about the solubility rules, which I have right here. Won't need to memorize these solubility rules, but let's go over some of these. You probably saw these in Chem 121, Gen Chem 1. All group 1 salts are soluble. So if you look at group 1 in the periodic table, the first element is hydrogen, which doesn't count as a metal. Then we have lithium, sodium, potassium, rubidium, cesium, and francium. We're saying that any compound that contains one of these metals is automatically completely soluble in water. And by soluble, we mean completion arrow, we mean 100% ionized. So lithium chloride would do this in water. It'll dissolve to the solubility limit. Sodium fluoride, which is often used in dental products, would do this. It's going to exist in solution not as the reactant molecules, but as ionized products. Potassium bromide is going to exist in solution as the cation and anion. We can go on and on. Any group 1 salt is soluble in water. All nitrate salts are soluble. So if you have any compound, it could be a transition metal like copper nitrate, copper 2 nitrate, or lead 2 nitrate. Often these transition metal compounds are insoluble in water. So if you're, say, studying lead in Flint water and you need a standard solution for comparison on the lead, then it would be nice to pick a lead nitrate compound because it's going to dissolve completely. It's going to exist in solution as lead cation and nitrate anions. You're going to have that lead freed up. All ammonium salts are soluble. You've seen this before in the buffer section. For example, ammonium chloride. Even though ammonium is not a metal, ammonium compounds act or behave the same way that metal chlorides or metal anion compounds behave. It's going to exist in solution as ammonium and chloride ions. None of the reactant is left over. In acetate salts, we've been using this improved formula here. You saw this with sodium acetate buffer. If you have such compound in aqueous solution, it's going to ionize 100%, and none of the reactants are going to be left over. So that's what we mean by these 4 solubility rules. If you see these compounds in the laboratory, you'll know that they completely dissolve up to their solubility limit. Not all compounds behave this way. Some compounds are called insoluble. To a chemist, insoluble doesn't mean 100% not dissolving. It means partly soluble. It means that tiny amounts of the salt dissolve. You'll see that these compounds dissolve according to an equilibrium. And because they're involved in an equilibrium, they have an equilibrium constant. We abbreviate that equilibrium constant by KSP. You'll see that SP stands for solubility product. So another one of the rules is that chloride, bromide, and iodide salts are soluble, except those of silver, lead 2, and mercury. So if you had a silver chloride solution in water, only some of it, only a tiny amount of it would actually dissolve. Most of it would be in the solid form. What did dissolve would do so according to this equilibrium. And so you might see a solid product at the bottom of a test tube. You'll probably see that the solution is cloudy as well because there's going to be these tiny silver chloride particles that can float around in the water. They're suspended in the water. Same with most lead compounds of the halides. They're going to be partly soluble in water, and same with mercury. Sulfate salts are soluble except those of barium, strontium, lead, and mercury. So that means that barium sulfate is insoluble in water. It means this would be its ionization equation. I think this one is used in the medical field. When someone has an x-ray of their intestines, they'll drink this substance. It'll coat the lining of the intestines and make an x-ray possible. We'll be writing more of these equations later on. Now, you don't need to memorize these. In fact, I've given these solubility rules with the tests before. But it'll be easy for you to differentiate soluble from insoluble compounds because if I tell you that something has a KSP, then you automatically know that it's insoluble. These are some of the polyatomic ions that you've seen before and that you'll see in later chapters. In this chapter, the polyatomic ions, just like for acids and bases, do not break down. They're not going to decompose into their components like nitrogen and oxygen or manganese, and oxygen. They're going to stay intact on both the reactant and product sides of the equation. They may be in different forms, but they'll be intact. Comparing soluble to insoluble salts. The soluble salts are classified as strong electrolytes. It means they're 100% soluble or ionized in solution. They're going to dissolve according to a completion reaction. The resulting solution is homogeneous and there aren't any reactants left. I've already written some of the equations like these two here, utilizing completion arrows. None of the reactants are left over. These compounds that contain a metal and a nonmetal are classified as salts. It means that the elements in these compounds on the reactant side are ions. So everything on the left side and the reactant side here is an ion. So we have sodium ions and chloride ions, calcium ions, and nitrate ions. In the dissolution, in the dissolving process to make them soluble, all that happens is that the ions break out of the crystal lattice or out of the compound and become independent. So for sodium chloride, a simple particle model would be +1 and -1 particles that are held together by an electrostatic attraction. Positive attracts negative. For calcium nitrate, it means that since calcium is in group 2A, we have a positive 2 calcium and 2 nitrate anions, which we could represent this way. And they simply break out of the crystal lattice to give independent ions. We start with ions and we end with ions. On the reactant side, the ions are held together in a compound by electrostatic forces, the ionic bond. Insoluble salts also contain metals and nonmetals, just like the soluble salts. Insoluble, as I pointed out, means they're partly soluble. They undergo dissolution, dissolving through an equilibrium reaction. Tiny amounts of products are formed. Most of the reactant stays as a solid reactant. The final reaction mixture is heterogeneous, meaning that there's a solid in the system. Most of the reactant or most of the compounds in the final product mixture are solids, and there are some dissolved ions in the aqueous phase. 2 phases, heterogeneous. This slide illustrates the dissolution of a soluble salt. This is sodium chloride. So I've shown a mini crystal of NaCl, 2 NaCl molecules. And you can see that the particle diagrams here show the positive and negative ions in that mini crystal. These are water molecules. The red is oxygen, the yellow is hydrogen. You probably remember that in water, it being a polar compound, the oxygen ends are partially positive and the oxygen end is partial negative. Positive attracts negative. So this is chemistry flatland. It's actually in 3D. What's going to happen is as many water molecules as possible are going to align with this mini crystal and surround it, hydrate it. So we might get this middle figure here where the negative end of an oxygen attracts a positive sodium, or a positive hydrogen end attracts a chloride, like that. And then what's going to happen is that thermal motion is going to help cause these ions to break out of their crystal lattice and become dissolved as independent ions. They're going to become hydrated. Each ion will be surrounded by as many water molecules as it can possibly attract. And so then with this picture, this is the chemical reaction equation. This is the first slide, and then this represents the last slide over here where the ions have broken out of the crystal lattice. We all know that sodium chloride will dissolve in water. If we put some in water, not too much, we can stir it up, where if we sit and wait, it's going to dissolve on its own. Because sodium chloride does dissolve in water, that dissolving process is spontaneous. and the standard free energy is a negative number. If we go back to our thermo section, this is the mathematical equation that explains how delta G varies with enthalpy delta H, entropy delta S, and temperature. Since we're under standard conditions, these superscript zeros mean 25 degrees Celsius. This temperature is going to be a constant at 298 Kelvin. And because the sodium chloride does dissolve on its own, we know that this delta G is going to be a negative number. If we look up the delta H for sodium chloride dissolving in water, it has a value of a positive 3.9 kilojoules per mole. So that delta H is moving us in the wrong direction, meaning it's positive, whereas we need a negative delta G to make this dissolution spontaneous. The only ways that we can get delta G to be negative is if we increase temperature, but we're not doing that. We have a constant temperature of 298, or if we increase the entropy change, delta S. If we have a fairly large positive value of delta S, the negative sign flips it to a negative, it'll overcome or outweigh, be greater than this delta H, and cause delta G to be negative. So what we're really saying here is that the reason for the sodium chloride dissolving in water isn't the thermal motion, isn't the amount of energy it's absorbing. It has more to do with the disorder that's produced in the system upon dissolution. So start out with, we have an ordered sodium chloride crystal, and we have a homogeneous phase of water molecules. At the end, the NaCl is broken up into independent ions, and moreover, those ions are dispersed across the entire volume of the system. They're mixed up. The final system is a lot more mixed up than the original. Each ion is hydrated. The hydrogen bonds between adjacent water molecules are somewhat broken up because these ions are between the water molecules. And the final system is a lot more disordered than the initial system. Because of this large delta S for dissolution, that drives the free energy change to be negative, making the dissolution spontaneous. Physical model for solubility. So as our example, we'll take silver chloride. You should know that silver ion always carries a positive 1 charge. That's something that you should just memorize. So for this transition metal, there aren't more than one oxidation state. So that's why we have the formula AgCl for silver chloride, because the silver is a positive 1 and chloride is a negative 1. We just need one of each to make the entire salt neutral. Because it's partly soluble, it's going to dissolve according to an equilibrium reaction. We start in the solid phase. We could have crystals in the bottom of the beaker, or we could have tiny particles of silver chloride suspended in the solution, making it cloudy. When it dissolves, the ions break out of the crystal lattice, giving a positive silver cation and the chloride anion, but these are in the aqueous phase. So we have two different phases. We have solid and aqueous, making the system heterogeneous. So when you write these equations, and some students have trouble with this, you need to know that the reactants are always in the solid phase, and the products are always in the dissolved aqueous phase, and that it's an equilibrium relationship. This material would be on your final exam, probably in multiple choice questions. So for an insoluble compound, the dissolving process is reversible. In other words, we can dissolve the silver chloride solid in the forward direction, but when the two product ions come together, they can actually precipitate to back form the solid. So it's a reversible process. The rate of the forward reaction equals the rate of the reverse reaction at equilibrium. Because we have an equilibrium, we can write an equilibrium constant expression. Remember that we don't include solids in a K expression, because why bother if that solid concentration is constant? Why bother measuring it and trying to use it in a calculation? So we're going to ignore the solid as always. Since we don't have any denominator, for that dissolution equation, AgCl solid, doing this. We only need the particles that actually dissolve. They're the ones that can change concentration. So this is the equilibrium constant expression. Because this expression is a product of the solubilities of two independent ions, we use the subscript sp for solubility product on this case. So you'll see that whenever you have a KSP, it means that we have an insoluble, a partly soluble salt that's dissolving in water. Waste treatment specialists use solubility an awful lot in determining how to actually precipitate harmful metals from drinking water. All right, so since we're doing our computations using molarity, sometimes chemists use the term solubility, and other times they'll say molar solubility. They mean the same thing. It means that the solubilities of these compounds or ions that are actually measured are going to be in molar units. That would be denoted this way for silver ion and this way for chloride ion, moles per liter or molarity. If, for example, the amount of silver chloride, we could say it could be in moles or in moles per liter, is Y. When some of it dissolves, we'll call that amount that dissolves X. We're going to get X moles per liter or X moles of silver and the same amount for chloride because they're produced in the same stoichiometric ratios, 1:1 here. The amount of silver chloride that we would have left would be Y minus X, the amount dissolved, but X is very tiny. These equilibria lie to the left because these KSPs are always much lower than 1. So X is tiny. Compare it to the initial amount Y. When we subtract, we almost get the same value Y back again. Y minus X is Y. Right? So then the solubility of this silver chloride is how much of it actually dissolved in moles per liter. So if we lose X moles per liter of silver chloride, then we form X moles per liter of silver ion and X moles per liter of chloride. That X is what we referred to as solubility or molar solubility. It's how much actually dissolved in the solution. Notice that this X can represent how much of the silver chloride dissolved because we have a 1 in front of the reactant and 1's in front of the product. So if 0.5 moles of silver chloride dissolved, we would get 0.5 moles of silver and 0.5 moles of chloride. Our silver chloride solubility could be either of these measured concentrations. So we could either measure the silver ion in solution or the chloride ion in solution or both and get the solubility of the silver chloride. Here's a pictorial diagram illustrated along with the chemical reaction equation. So the chemical reaction equation for silver chloride dissolving, again, we started with the solid. Through an equilibrium, it dissolves into silver and chloride ions, and then the back reverse reaction, back forms the precipitate. We could imagine that we had a silver chloride crystal in solution. The illustration would be that only a tiny amount dissolves. So in the final picture, which represents the products, I only show one molecule dissolving to give ions. In reality, it'd be like 1 in a million actually dissolved. So you really do get tiny amounts of these dissolved ions in solution. The forward reaction is dissolution, dissolving. The reverse reaction is precipitation at equilibrium. Those rates are equal to each other. Okay, rate forward equals rate of reverse. And these concentrations, silver ion and chloride ion concentrations are equal, representing the dissolved ions. That's going to equal to a constant. Remember, one of the criteria for equilibrium is that the concentrations are constant with time. So once the equilibrium sets up, and for some of these salts that dissolve in water, the equilibria could require weeks to actually set up. Usually, this is one case where the equilibria aren't set up extremely quickly. Sometimes you have to make a solution and shake it over a period of weeks, okay? And then do a test to see when the concentration has come to a constant. Here's an example of actually computing solubility in moles per liter. Given a solubility value from a table in grams per mil. So as I mentioned before, you often see when you look up solubilities in tables that they're given in like grams per milliliter. Solubility may seem like a boring subject, but it's important in wastewater treatment. It's important in the drug industry as well, because in pharmacology, you actually have to know how much of a drug actually dissolves, say, in a bloodstream. We're working in water solution, which is pretty simple. It's going to be a lot more complicated in blood. But for that calculation, if we know that the solubility of silver chloride is 2 times 10 to the negative 6 grams per mil of solution, it'd be what? Micrograms. We're going to convert mils to liters using this conversion factor. That'll put liters in the denominator. Then we compute the molar mass of silver chloride. Silver, there on the periodic chart, toward the middle on the right side, looks like its atomic weight is around 108. Chlorine, you probably know, around 35.5. We add those up. Exactly, we get 143.32 grams per mole. Divide by the molar mass. We're going to end up with the solubility in moles per liter for silver chloride, 1.4 times 10 to the negative 5th molar. So that means that that's equal to the measured, if you measured the concentration of dissolved silver and chloride ions, it should be 1.4 times 10 to the negative 5th moles per liter. Given these solubilities in moles per liter, we can back compute the KSP by the product of the 2 ion concentrations, the solubility product. Well, here it is here. Square didn't come out in equation editor very well. We're going to square this number here. We get around 2 times 10 to the negative 10th for the KSP. As I pointed out, these KSPs are always far less than 1, meaning that most of this AgCl is going to stay in the undissolved solid, and we're going to get very tiny amounts of dissolved ions. Still is important because many of these transition metals especially are toxic. They end up in the environment. They pollute streams, especially in urban areas where we used to have lots of factories and mills, steel making and chemical companies. I think up in Buffalo, New York, which I understand is getting around 3 feet of snow today. Lucky that you had your game last week. I watched that game. It was a good game. I actually used to live there. I think we had a snowstorm in April where we got 3 feet of snow once. It was horrible, but there's a lot of neat parks around there. So anyway, in Buffalo, where they closed most of the steel mills, I think back in the 80s, they closed them down and like 20,000 people lost their jobs in one day. A lot of the rivers are polluted with heavy metals that came from the industries. And the Buffalo River sediment is so polluted that the National Institute of Standards actually picks it up. They actually collect it, and they sell it as a heavy metal standard for chemists. Buffalo River sediment. I've used it before. To further illustrate dissolution, I've taken a crystal. This could be silver chloride, or it could be any +1, -1 insoluble salt, like barium sulfate. So we put it in water. I haven't shown the water molecules. If we were the size of one of these ions, it would seem that this wall would stretch on forever and forever. This is 2 dimensions, but actually it's 3D. So most of the particles in a solid like this, in a crystal lattice like this, are going to exist in the interior of the solid, and they're going to remain untouched because the reaction is going to occur only at the surface. So the only part of this compound that we lose are surface molecules, and that's another feature of a heterogeneous reaction. It's one that occurs at a surface. But we have huge amounts of this in water. So as we saw before, some of the particles are going to break out of the crystal lattice to start dissolving. those ion concentrations are going to build up to a certain level. They're going to be hydrated by water molecules. When they get too close, they're going to start attracting each other and cause the reverse precipitation reaction to occur. The net result is that we get tiny amounts of dissolved ions in solution at a constant concentration that's stable with time. And that represents solubility. Let's write some solubility equations for some insoluble compounds. You're told to look up a KSP value, so you know that every one of these compounds here is going to dissolve according to that template that I gave you before. And at the end of the course pack, I have actual KSP values. So we want to write some equations here. So for silver bromide, remember, we said that silver only exists as a positive one cation. Bromide is a halogen with a -1 charge. We only need one of each to get a neutral compound. So our reactant is AgBr. And we know that it's insoluble, so it's going to start in the solid phase. It's going to dissolve through an equilibrium. And on the product side of the equation, since we started out with two ions electrostatically attracted to each other and held in a solid, on the product side, they've just broken out that crystal lattice, so now those ions are independent. Remember that we don't show charges for an ionic compound formula because we can get the charges from what we know in the periodic chart, from either the group number, like bromine is in group 7A, so it's a -1, or from looking at a table to get the charges on silver, or being told what the charges are using, say, Roman numerals. Silver only has one oxidation state, so we automatically know it's a positive one. So that's our reaction equation. Our KSP expression is going to have a value of 1.8 times 10 to the -10, and it's going to be the product of the dissolved ion concentrations in moles per liter. Square brackets meaning molarity. That's our first one. Second one is zinc sulfide. You might know it, but zinc normally exists as a positive 2 cation. There aren't very many instances where it doesn't. So zinc starts out as a positive 2. I would tell you that on a test. Sulfur is in the oxygen group. All the elements in the oxygen group have an oxidation state of a -2. So positive 2 balances a -2. We only need one of each in our ionic formula. So our formula is ZNS. Started out as a solid, equilibrium, dissolution, zinc 2+ cation, and sulfide, anion. Sulfur compounds are a real problem. They have bad odors. You know, if you put some of this in water, you're probably going to form hydrogen sulfide, which is very poisonous. So whenever you use a sulfur compound, you have to have special ways of handling the waste. You don't want to throw any of this stuff down the drain. It's going to get into the drain system and contaminate it for quite a long time. There'll be the smell of hydrogen sulfide throughout an entire building. So you need to be careful with sulfide compounds. The KSP expression for this, 2 times 10 to the -22. Again, we ignore the multiplicative product of the zinc ion molarity. Calcium carbonate has many different forms in geology. Marble, which is used in buildings, or what we have around here, limestone, low-grade limestone used in pavement. The carbonate polyatomic has that formula there. Calcium is in group 2A. It's that. Again, we just need one of each, so our reactant is CaCO3, solid, equilibrium, calcium 2+, and carbonate. Remember, I said polyatomics don't break down. We have carbonate, CO3 on the reactant side, and the same thing on the product side. KSP for this. Each one to the power of 1 because the stoichiometric coefficients are 1. Calcium fluoride. Calcium group 2A. Positive 2 fluorine group 7A. -1. We need a neutral compound to begin with. To balance a +2, we need 2 -1s. So our reactant formula is CaF2, solid. In geology, I think they call this fluorite. It's fluorescent, meaning that if you shine ultraviolet light on it, that it'll glow. It glows blue. I think that you can actually find some of this in this area in some of the rock pits that they have. And I think our geology club sometimes goes down and hunts for it in maybe Michigan. The KSP for this, 3.2 times 10 to the -11. It actually forms perfect octahedral crystals. Aluminum hydroxide, group 3A for aluminum, so it forms a +3 cation. Hydroxide, you know, is -1. To balance a +3, we need 3 -1, so the formula for the reactant is AlOH3. And our KSP value, silver sulfate. Sulfate is a polyatomic with a -2 charge. Silver, we said, is always a +1. We need 2 +1s to balance the -2. So the reactant formula is Ag2SO4. Ag plus, this time squared because of the coefficient of 2, times the sulfate. Polyatomic didn't break down. Sulfate on both sides. And the KSP for this. Right, so now that we've written equations and KSP expressions, we want to compute the actual solubilities of some of these compounds in water. So to do that, I have some examples. This is the first one. This is for zinc carbonate, which would be this formula here, ZnCl3. It's going to dissolve according to this equilibrium equation. Our corresponding KSP expression is going to be this here. Having looked up the value or given the value of that KSP as being 10 to the -10. To solve for the concentrations in equilibrium, we're going to reduce this 2-variable expression to 1 variable in X. So we look at the equilibrium relationship and we notice that we're going to form equal number of moles of the zinc and carbonate. If we form equal number of moles, the same stoichiometric ratio, then the concentrations will be the same as well. So we let one of them equal to X moles per liter, then the other is going to be X moles per liter as well. We can take this expression, substitute X twice, we're going to get the KSP values X squared. We take the positive square root of the KSP and we compute X, which is 10 to the -5 molar. That's going to be the solubility of the zinc carbonate in water. It's also going to be the concentration of dissolved zinc ion and dissolved carbonate ion. So in other words, the solubility of the zinc carbonate is the same, or calculated values in the same ratio. If we lose X moles per liter of zinc carbonate, then we form X moles per liter of either product ion. So with that under our belts, why don't you try the next problem, problem number 2. It's going to be on page 502. You can set this one up and solve it in the same way. Let X be the solubility of the silver chloride. It's going to be equal to the measured dissolved silver ion or chloride ion concentrations. If X is the silver ion concentration, it also represents chloride, so we get X times X, or X squared. X is going to be the positive square root of the KSP, is 1.34 times 10 to the -5 molar. That's the molar solubility, equal molar, or just solubility. It's also equal to the dissolved silver ion and dissolved chloride ion concentrations. In other words, if we lose X moles per liter of silver chloride, we're going to form X moles per liter of either product ion. In the next example, we're going to change it just a little bit and look at a slightly more complicated salt here, nickel 2 hydroxide. You may remember that for many ionic compounds involving transition metals, that because those transition metals can have more than one oxidation state, that we designate the oxidation state using Roman numerals. Nickel is one such compound, usually exists as a positive 2 ion. So nickel, Roman numeral 2, means nickel with a positive 2 charge. We know that hydroxide is a negative 1. So to balance a positive 2, we need 2 of these hydroxide. Hence, our nickel hydroxide formula is NiOH taken twice. And then this would be the resulting dissolution equation. In this particular case, the nickel ion is 1-to-1 with the reactant. So the solubility of our nickel 2 hydroxide is going to be equal to the measured concentration of nickel ion in solution, because they're 1-to-1, but not equal to the hydroxide because there's a 2 in front of the hydroxide. So given this equilibrium relationship, this would be the corresponding KSP of 2 in front of hydroxide. We have to square it. To solve this one, you can solve it in many different ways algebraically, but I think it's easier if you start with one of the products whose stoichiometric coefficient is 1, and say let X equal to the concentration of dissolved nickel. For each mole, or for each X moles per liter of nickel ion that's formed, we're going to form double the amount of hydroxide because of the coefficient of 2. So we could say that the X would be the dissolved nickel ion concentration, and that hydroxide is going to be 2 times that dissolved nickel ion concentration, or 2X. So when we plug that into this expression here, some students have trouble looking at the algebra. So remember that you could take this formula and you could rewrite it this way. When you square something, it means you multiply that something by itself. Then we could substitute in X for the nickel, 2X for the hydroxide a second time. We're going to get 4X cubed out of this. So the other way of doing it, it would be X and 2X quantity squared. The hydroxide is 2X. We have to square that quantity 2X. So we're going to end up with this for our reduced KSP expression, having reduced 2 variables in nickel and hydroxide to 1 variable in X. We first solve for X cubed by dividing the KSP by a 4, 1.5 times 10 to the negative 16, and then find X by taking the cube root of this result right here. You could do that cube root in a couple of ways. You could write it in conventional notation, or since cube root means to the 1/3 power, you could use this instead. Remember that 1/3 is 0.333, infinite number of decimal places. If you actually use this method here, 1/3, you could actually just plug this into your calculator, the decimal number, but you want to use a lot of significant figures so that you don't have a round off error. You got a cube root key on your calculator, or in mine I have X root of Y. You use that, or you can use on my calculator Y to the X, where the X is 0.333. At any rate, when you take that cube root, you get this X. That X represents dissolved nickel. For every nickel ion dissolved, we lose that amount of nickel hydroxide. So the solubility of nickel 2 hydroxide is the value of X, which is this, which is what we're looking for. And then for using the calculator, I have this note here. I've shown some of the keys. You might have to press equal or enter key here. Your calculator may be different. On mine, this is how you actually enter the scientific notation for this number here. And then to take the cube root, I need to use the second key, the x root of y key, 3 for x equal, I get that number there. Plug it in, you could do y to the x key, x, which is this number here, and then equal, let me try that, 1.5 double e negative 16, y to the x 0.333. Second scientific, yeah, I get that result there. All right, try this one here for fluorite, that fluorescent mineral. 3.2 divided by 4 is 0.8, which gives us 8 times 10 to the negative 13. All right, so that's x cubed. X is going to be the cube root of that, or you write it as it's a 3. We'd always check this number. We could take it and cube it, and we get this back again, so it works. Alrighty, then on the next page, you can take a look at that. Number 5. This one is on tooth enamel. We have a compound called hydroxyapatite, Ca5PL4 3OH, sometimes abbreviated H. It's the main component of tooth enamel. Actually, like I've got, as I mentioned, abbreviated HA. Okay. And this is a formula that's been determined. Tooth enamel is a lot more complicated than this compound, though, because it turns out that there's several different crystalline phases in tooth enamel that really complicate the chemistry of it. The companies like Procter & Gamble, Colgate, or some of the others actually have chemists, PhD chemists, who study these compounds. Some dental schools are interested in this research as well, so they'll hire PhD chemists as research people. So this is HAP. It's a salt, it's an ionic compound. So its corresponding dissolution equation is this. We have ions inside the reactant. They simply break out on the product side, but in the dissolved aqueous phase. So we're going to get 5 calcium ions, 3 phosphates, and 1 hydroxide out of this. Our corresponding KSP expression, given this is the value for the KSP, would be the calcium ion concentration to the 5th power, phosphate 3rd to the 3rd, and hydroxide to the 1st. So reduce this one to one variable in X. It's easiest if you start with hydroxide because its coefficient is 1. Let X equal to the dissolved hydroxide concentration. Then the dissolved phosphate concentration is going to be 3 times X, and the dissolved calcium concentration is going to be 5 times X. So then what you need to do is you substitute for calcium. For this whole thing here, you're going to substitute 5X, which you're going to take to the 5th power. For phosphate, it's going to be 3X to the 3rd times X for hydroxide. So that's how you get the KSP expression for this. Here it is over here. I've separated the X's from the coefficients. I'm going to end up with this here. When you multiply numbers that have the same base, you can add the exponent, so we get X to the 9th. When we multiply out all the numbers, we get this coefficient, 84,375. We solve for X to the 9th by dividing the KSP by the coefficient. We get this number here, and then we have to take that result to the 1/9 power to get the X, which is the solubility of the HAP in water. 2.7 times 10 negative. This is at neutral pH. All right, so it all changes if you're in an acidic solution. If you're bathing your teeth in phosphate cola, which is very damaging. So what we're going to do next is we're going to take this HA and we're going to substitute a fluoride ion for the hydroxide. So we simply get this here. And this, you might think, is logical to be called FAP, fluoroapatite. So when you use these dental rinses that contain fluoride, or if you use fluoride toothpaste, some fluoride toothpaste contain stannous fluoride. I think others might contain sodium fluoride. The rinses probably contain sodium fluoride. I know that some dentists actually put a fluoride glaze on teeth to protect them. You have to be careful about doing that. You probably couldn't do it yourself. You have to have the right compound to actually do it correctly. Otherwise, you can cause your teeth to turn brown. We're going to do the same calculation on FAP as we did before. We're going to write the ionization equation, the corresponding KSP expression, and reduce it to one variable in X and compute the solubility of FAP in water. So for part A here, Ca5, PL4, 3, fluoride in the solid phase undergoes dissociation to give 5 calcium again, 3 phosphates as before, dissolved in the aqueous phase, and instead of hydroxide, now we have a fluoride in solution. Alrighty, so then our corresponding KSP is going to be 5 times 10 to the negative 61. Notice that the KSP is a lot lower than for HAP. HAP was around 10 to the negative 37. This is 10 to the negative 61. So the reason for using these fluoride rinses is that the fluoride can actually go into the tooth enamel and substitute for the hydroxide, giving a less soluble compound, protecting the tooth enamel. You get calcium ion to the 5th power times phosphate, 3rd times fluoride. And then this would be X, this would be 3X, this would be 5X. So we're going to get actually the same coefficient as before, 84,375 times X to the 9th power. X to the 9th is 5.1 times 10 to the negative 61 divided by this. We get 6.044. X, which represents the solubility of fluoroapatite in water, pH 7, is going to be the 9th root of 6.044 times 10 to the negative 66. So I'm going to do, let's see, second x root of y, 9 equal, scientific notation, 5.67 times 10 to the negative 8 molar. Compared to HAP, that solubility was 2.7 times 10 to the negative 5th molar. So the fluoroapatite has a much lower solubility by a factor of at least 1,000, rendering the tooth enamel more resistant to dissolution. Anybody in a dental program here officially? No? Who knows what city in the United States was the very first to fluoridate its drinking water? Turns out it was Grand Rapids, Michigan. Okay. All right, we'll stop here with solubility. We have a few minutes left, so we can maybe look at that last homework assignment. Let me see if I can pull up a blank page. All right, so in that homework assignment, the very first question involved acetic acid and sodium acetate, and the ionization equations in part A would be this for the acid, equilibrium, dissociation. I have the answer key up there on Canvas under announcements. So this is one equation that you have to write. It's the equilibrium reaction. And the other one is for the salt where we replace the H with the sodium. We have the same conjugate base in each one. This is going to be a completion reaction. You have to know which one is which. The salt dissolves according to completion. The weak acid by equilibrium. And you're supposed to compute the pH using HH, Henderson-Hasselbalch, for different concentrations. So some of the students mix the concentrations up. So it might be easier for you if you write them down for what they actually are given as. It says the acid in the first one is 0.2 molar, which turns out to be same as the sodium acetate. So this one, it didn't matter. The pH via Henderson-Hasselbalch would be pKa, 4.77 plus log, product over reactant. It's this equation here. So the product is acetate. I might ask you to write the equation using chemical formulas. These are both 0.2, okay? So the ratio is 1, log of 1 is 0, so we get 4.77. When the moles or concentrations of the conjugate base and the acid are the same, the pH is equal to the pKa. And the next one, C, you're given that and this might help you to actually write it out so that you don't mix them up. The acid concentration is 0.2, and the salt is going to be 0.02. So the pH, again, is 4.77 plus log, product over reactant, conjugate base over acid. So in the denominator, we have 0.2, in the numerator, 0.02. You can see that this ratio is 1:10. You can calculate it out, right? You can get 4.77 plus log of 10 to the negative 1, which subtracts. There's going to be more acid than conjugate base. The acid is 10 times the conjugate base, so the pH should be lower than the pKa, which it is by 1 unit. Each factor of 10 means a pH drop or increase of 1. And then D here, we just have the reverse. pH is 4.77 plus log. The denominator is the acid, 0.02. The numerator is the salt, which is the same as the conjugate base. You can see that the numerator is 10 times the denominator, so we get 4.77 plus log of 10. Log of 10 is 1, 5.77. When we have more conjugate base than acid, the pH should be higher than the pKa. So then what happened here? Right, so then for the second part here, if I can page down this thing. For the second part on the ammonia base, you're probably going to see one on ammonia on your examination, okay? This is for ammonia and ammonium chloride. So the ammonia is a weak base. It's going to undergo an equilibrium dissolution. But remember, since the ammonia doesn't contain hydroxide, you have to add water, mandatory, as a second reactant to form ammonium and hydroxide. So that's the weak base equation. The salt, ammonium chloride equation is going to be completion. Weak base is equilibrium. The salt is completion. We're not going to use Henderson-Hasselbalch for this. Don't bother trying to memorize the equation. I won't give you credit if you do use it. The KB for this, we're going to use the equilibrium to compute. So that KB is given as 1.8 times 10 to the negative fifth. That's going to be ammonium from this first equilibrium times hydroxide over ammonia. Can't use x squared here because we have the ammonia given as one component at 0.2 molar in part B, and the ammonium chloride is 0.2 molar. But the hydroxide is not the same as ammonium. Since we're given the ammonium chloride at 0.2, it's at a different concentration than hydroxide. So for this particular case, it's 0.2 over 0.2 times hydroxide, sulfur OH, get a POH, and then a pH, which is going to be higher than 14. For part C, you get 1.8 times 10 to the negative fifth. That's going to be equal to the ammonium concentration, the ammonium chloride, which is 0.02 times hydroxide over the ammonia, which is 0.2. So this is 1/10. You have to multiply the Kb by 10. The hydroxide is 1.8 times 10 to the negative 6. 1.8 double E negative 6. Log of that gives us a POH of 5.74. Subtract from 14 gives us a pH of 8.26. You're going to have to do that on your test. I put some more notes under announcements for the course pack and for pre-problems.